Hello, and today we are going to discuss how to solve image recognition, face recognition problem in using linear algebra, and specifically how to determine if two people are connected with each other biologically or not. Okay, as an input for our application will be two images with faces. Okay, and suppose it is mom and it is son. What are we doing? We just cut the image to the face size in both ways, and we grayscale that. Okay, and suppose that face like cutted image is 4x4 pixels, so we can represent it as 4x4 matrix A, B, C, D, E, F, and so on. Like it's going to be 4x4 matrix. And we started to preprocess it. How to preprocess it? First of all, we should flatten it. What does it mean? We just compress that 4x4 matrix into one single vector that looks like that, and its size is 16x1. Okay, and after that, we know that as we grayscaled the image, we know that all the elements inside the matrix is going to be in range from 0 to 225, and it's going to be much more comfortable to normalize it. It's going to be again a 16 by 1 vector, and after normalizing, each element of the vector will be in range from 0 to 1. How to do it? We just should multiply it by the maximum number. In our case, it's 255. Yeah, and so on. Okay, that's the first stage of first step for our preprocessing. And for now, we should consider the case when we have a bunch of those flattened and normalized vectors. For example, we have a bunch of 3 images, and the size of the matrix will be 3 by 16. It is example just. Okay, and here we have 3 rows which contain 16 elements. And what is crucial for us here is to find mu matrix such that if those elements are equal to x, y, z, we should in mu matrix we should just get average of all the columns. For example, the first element will be average for the first column, and it is like that, just average. And we are doing for all the columns, and the mu matrix is going to be 16 by 1. And after that, we are getting centered x. What does it mean, centered x? Okay, it has that formula because x is describing the whole image. But we are not interested in that. We just interested how it differs from just average face. And the mu is in this case it just describing that average face from that bunch of images. In our case, it is just 3 images. So, okay, after that, we use PCA here. What the PCA here? For what purpose? Because PCA will help us to distinguish how distinguish those significant features of the face. It includes SVD, and SVD says us that our centered x is equal to some matrix U, sigma, and V transposed. We just wrote our, for example, big centered matrix X as 3 simple matrices. It is crucial for us here to know about those 2 matrices. Sigma is a diagonal matrix which contains, for example, we have 3 crucial features of face: sigma 1, sigma 2, and sigma 3. Okay, and those sigmas they say us how the feature is significant for us, and it is composed in that way that sigma 1 is bigger than sigma 2 and sigma 2 is bigger than sigma 3. So the most significant is to the left, according to diagram. Okay, and the matrix V is just that matrix contains eigenfaces, and those eigenfaces they represent our those features as vectors, because that X just contains the difference in pixels, but V contains like vectors for those features. So for example, our V is equal to be A, B, C, D, E, F, G, H, I. And for example, our K is 2. It's just, okay. And for what reason we define that K? Because it is not always necessary for us to know all the features. And as we know that our, for example, sigma 1 and sigma 1 is the most significant, we can just get rid of least significant features in order to get rid of noises and some rubbish. Okay, and we define VK, which contains vector V1 up to VK. So in our case, our V2, because our K is 2, is equal to A, B, D, F, G, H. Okay, and then we should transpose it. So V2 transposed is equal to A, D, G, and B, E, H. So after that, as we have such a vector, we can define our embedding, and our embedding will be Z, and those that will equal to V2 transposed multiplied by our image of mother, X mom, minus our mean that we grabbed from here. Okay, and in our case, as we consider only two most significant features, embedding will be just a vector 2 by 1 with some a and b constants. Let's consider of a. If a will be greater than 0, so the person would be more likely to have that feature. For example, if our sigma 1 is a shape, like describes a shape of face, and the sigma 2 is skin color. So if a greater than 0, it means that the person is more likely to have exactly that one shape. If not, a will be less than 0. Okay, and that applies also to b. Okay, and we have, for example, that embedding for mother and from son. Okay, how to distinguish for now using those embeddings if they're connected with each other biologically? We just subtract those two matrices, and then the result of that will put that as an input to our decision tree. Why? Because from here it is also 2 by 1 vector, and it will decision tree will help us to find those thresholds after which we can say if they are connected biologically or not, if they have like the same features of face or like related features of face, yeah, because they cannot be identical. And after that, our decision tree has output two classes, 0 or 1. 0 describes that they are not biologically connected, and 1 describes if they're biologically connected. And that's it.